I'm Rajesh Uppal, Director IDST. We bring sharp insights and foresight on defense, security, and emerging tech. Let's dive in.
In 2025, the United Nations declared it the International Year of Quantum Science and Technology, acknowledging the global surge in quantum innovation. Quantum computing is no longer confined to research labs. It's emerging as a powerful tool for solving some of humanity's most complex computational challenges. Unlike classical bits, which are strictly 0 or 1, quantum bits, or qubits, operate in superposition and harness entanglement, allowing them to perform calculations simultaneously in ways classical computers can't. Different qubit technologies are tailored for different goals. Trapped ion qubits use charged atoms suspended in electromagnetic fields, offering extremely high fidelity and full connectivity, perfect for testing new algorithms. Superconducting qubits rely on circuits cooled near absolute zero and excel at scaling toward millions of qubits. Spin qubits in silicon exploit the intrinsic spin of electrons within semiconductors, promising smooth integration with existing chip-making processes. And photonic qubits use particles of light to carry information, providing inherent stability, room temperature operation, and massive potential for scaling. While qubits are fascinating individually, they need to be orchestrated within quantum chips, the custom processors designed to control, entangle, and read qubits with precision. These chips transform the strange physics of quantum mechanics into practical computation. They're the backbone of today's quantum computers, enabling researchers to tackle problems that would overwhelm classical machines. But in 2025, quantum computing is no longer just about having more qubits. It's about precision, error control, and scalability. What makes one chip better than another depends on the task at hand. Some are ideal for algorithm testing, offering unmatched fidelity. Others are designed to scale to millions of qubits. Researchers evaluate chips using key metrics. Qubit count determines the complexity of computations possible. Gate fidelity measures how accurately qubits perform operations. Connectivity reflects how freely qubits interact. Coherence time shows how long qubits maintain their state before errors accumulate. And scalability assesses whether the system can grow to handle real-world problems. A chip isn't the best just because it has the most qubits. It's about balancing reliability, efficiency, and practical usability. Leading the charge in experimental platforms is Microsoft's Majorana 1, a daring bet on topological qubits. Using exotic Majorana 0 modes, this chip encodes qubits with intrinsic error resistance, sidestepping many challenges that plague other architectures. Though it hosts only 8 qubits today, its design is tileable and scalable, potentially supporting a 1,000,000-qubit system. Majorana 1 aims for real-world impact in molecular catalysis, materials science, and self-repairing smart systems by 2027. Meanwhile, IBM continues its dual-path approach with 2 flagship superconducting processors. Condor, the first chip to cross 1,000 qubits, demonstrates sheer scale with the modular architecture and improved connectivity for multi-chip integration. Heron, with 133 qubits, prioritizes precision, using tunable couplers to suppress crosstalk and enhance fidelity. Together, they exemplify IBM's vision of quantum-centric supercomputing, blending scale with accuracy for tasks in optimization, AI, and machine learning. For ultimate fidelity, Quantinium's H2 sets the benchmark. Using trapped ion technology, H2 achieves 2-qubit gate errors below 0.1%, with full connectivity among its 32 qubits. Its logical encoding supports error resilience and early fault-tolerant demonstrations, proving that fewer high-quality qubits can outperform larger, noisier systems for many real-world applications. SpinQ Titanium demonstrates China's industrial-focused approach. Superconducting qubits on ultra-pure silicon achieve over 100 microseconds of coherence, with 99.9% single qubit and 99% 2-qubit fidelities. Vertical integration ensures tight control over design and fabrication, while modular architecture allows upgrades and scaling without rebuilding the system, ideal for AI, pharmaceuticals, and finance. Google's Willow chip pushes the frontier of error correction. Building on the Sycamore lineage, it uses 72 superconducting qubits with real-time error correction protocols that extend coherence and preserve logical states. Willow demonstrated quantum supremacy on random circuit sampling, laying the groundwork for Google's projected 1,000-qubit system in 2026. Rigetti's Aspen-M targets mid-scale modular deployment. Its 80 qubits in a lattice structure allow hybrid quantum classical computation, suited for optimization and quantum chemistry, and are accessible via cloud platforms for rapid prototyping. Intel innovates at the hardware interface. Horse Ridge 2, a cryogenic control chip, sits just millimeters from the qubits, reducing latency and improving fidelity. Tunnel Falls introduces silicon spin qubits, ultra-compact and CMOS-compatible, promising dense integration with classical systems. Together, they highlight Intel's dual strategy: high-performance control plus scalable, industry-ready qubits. Oxford Ionics' EQC platform reimagines ion traps with laser-free electronic control, achieving record fidelities of 99.9992% for single qubits. By fabricating with CMOS-compatible processes, EQC merges semiconductor scalability with ion trap precision, making quantum computing more manufacturable and practical. PsiQuantum takes a bold photonic approach, using single photons as qubits manipulated through integrated silicon photonics. Operating at or near room temperature, these chips promise massive scalability and inherent stability. PsiQuantum is aiming directly for a 1,000,000-qubit fault-tolerant quantum computer, skipping incremental steps to industrial-scale quantum machines. Global efforts show that emerging national programs and startups are also shaping the field. China's rapid advances reflect a national push to closely follow and sometimes rival U.S. leadership in quantum technology, investing heavily in both scale and application-specific performance. Their Zuchongzhi 3 processor, with 105 superconducting qubits and high connectivity, is already challenging Western benchmarks in speed and reliability, showing that China is a serious contender in the global quantum race. China continues to closely track U.S. advancements, scaling systems like the Tenyan 504 platform and pushing qubit fidelity higher with each generation. Europe's Pascal focuses on precision, modularity, and specialized applications, demonstrating that different strategies, scale versus purpose-built performance, can coexist. Access models are evolving too. Cloud-based platforms like IBM's Qiskit runtime allow anyone to experiment on mid-scale quantum machines, while modular QPUs from companies like Quantware and specialized D-Wave annealers provide on-premise deployment. Quantum computing is no longer exclusive to elite labs. Researchers, developers, and enterprises can build, test, and scale applications today. Looking ahead, the next 5 years promise transformative milestones. Logical qubits are expected to scale beyond 50 interconnected units, reducing error rates, while quantum interconnects will link chips across distances, forming distributed quantum computing networks. Economically, quantum computing could generate over $1 trillion by 2035, with high-impact applications in drug discovery, climate modeling, logistics, and more. At the same time, it drives urgency in post-quantum cryptography, as conventional encryption will be challenged by these powerful machines. The quantum computing landscape is dynamic, and no single chip dominates. But across continents and architectures, we see a convergence toward practical utility. Chips like IBM's Condor, Quantinuum's H2, Google's Willow, Microsoft's Majorana 1, and China's Zuchongzhi 3 are not just faster, they are redefining what computation can achieve. In 2025, performance, error correction, and architecture matter more than raw qubit count. The next generation of quantum chips will transform entire industries, unlocking possibilities from cryptography and AI to climate solutions and drug design. As Microsoft's Dr. Chetan Nayak aptly says, we're not just building faster computers, we're inventing a new science of problems. The quantum revolution is here, and its chips are the engines powering a new era of computation. Thanks for watching. Subscribe, follow, or visit IDSTH.com for more cutting-edge defense and tech insights. See you in the next one.